Okay, now I gotta say, I stressed last week, got denominators in an equation, multiply both sides by denominators. Okay. More specifically, multiply both sides by the least common denominator. Keep the numbers lower. Okay. But as long as if you multiply by all the denominators, it's going to work. There's an advantage to the least common denominator. Okay. So let's just demonstrate how this works. I'm not going to talk about the first equation. I think everybody's good there. You know what the operations are. You're showing them. You're showing the steps, and I'm very happy to see that. Okay. If you want to make me really ecstatic, you can start multiplying the equations by the denominators. Okay. So one thing that you right now lack for being able to pretty much solve any linear equation. That's an accomplishment. Okay, so let's get that piece in there. Okay, so let's say we've got 5/3 x minus 3/7 equals 5. Okay. Well, we see a denominator here, 3. I multiply both sides by 3. This, so we've got 3 times 5/3 x minus 3 times 3/7 equals 27. What is on up here? I think I've got room to write it. Probably mess it up. Probably got off the edge of the board there. Okay, so you got 3 times 5/3 x. Well, I'm going to do one more step here. I've got 3 dots here. Meaning you write that as 3/1 times 5/3. Arrange that. 3/3 times 5/1. Because when you multiply the numerators and denominators, it's going to come out the same. Divide the 3 by the 3, and pretty quick you're going to get 5. You do want to see those steps by asking. Otherwise, you're going to start crossing things out, get in the habit of crossing things out, start crossing things out that don't get crossed out. Okay? I don't like crossing out. At this stage, later on, it's a real convenience. Okay, anyhow, we got 5x minus 9/7 equals 27. Everything in the equation got multiplied by 3. And to be consistent, I should have written instead of 27. Yeah, just keep everything in multiplication form in this step. Then in this step, we do all the multiplication. Now multiply 3 by 9 to get 27. I'll probably leave it the way I had it. But you could do it in either form. Okay? Because everything is equivalent. Everything in this equation, the whole side here has been multiplied by 3. We applied the distributive law. We didn't just multiply the 5/3 x by 3. We multiplied both sides by 3. So the distributive law ended up multiplying the -3/7 by 3 to give us 9/7. Okay, so we got 5x minus 9/7 equals 27. It's not a difficult step if you think to do it. It's very simple. If you just put a 3 in front of this side and a 3 in front of this side and do what it says, you immediately get to this. And this is much simpler than this because you only got one fraction left. Now, normally we'll take care of both fractions at the same time. I'll show you how that works. And I don't think you'll have any trouble. But see, again, we've got a denominator, right? What do? We multiply both sides by that denominator. So we do 7 times 5x minus 9/7 equals 7 times 27. Okay. Now 7 times 27, I will go ahead and multiply. That's 189. Right. And 7 times 5x is 35x. And I've got some dots. Okay, 7 times negative 9/7. Well, I better write it 7 times 9/7. So really, not many dots there. And I didn't multiply. I didn't write out 7 parentheses 5x like I did here. But we understand that we're multiplying 7 by 5x to get 35x. I wrote this multiplication because it's a multiplication of fractions. Multiplication of fraction by whole number. That's where your dots come in. 7 over 1 times 9 over 7. The same as 7 over 7 times 9 over 1. Just switch those denominators. Makes no difference because when you multiply the numerators and multiply the denominators, you get the same thing both times. Don't understand what I'm saying? Review the video. Okay? Make yourself a note what that is in the videos. Find it. You see it a number of times. And you really, when you're taking notes, you really want to write stuff like that down. And you really want to say, okay, this is really important. Put a circle around it, put it there, even look at the clock. What time is it? Gives you a clue about which video to look at and around what time it had occurred. Okay. Okay, so 37x minus 7 times 9 over 7, that's just minus 9, that equals 189. 7 or 7 times 9. And then here's 7x is 198. That's 198 over 137. Then you check. I'm going to check. Okay, now I multiply both sides by 3 and I multiply both sides by 7. We do that all at once. So I can start again. I'm going to write out the first couple steps and ask you to finish it. Okay. Got 5/3 x. Well, okay. 5/3 x minus 3/7 equals 9. Gives 3 times 7 times 9. I multiply by both denominators all at once, so I don't have to do this in as many steps. So from here, work it out and show all the details. And of course, I'll come around and coach you on if you need it. Okay, as I said, people have difficulty here. Okay, not everybody. Half the class had difficulty, half the class did it right. And some people, I think, even showed every step. We have to understand steps because we have to understand multiplication of fractions. So as I said, go back and do that assignment again without looking at anything. Okay. If you can't do an assignment without looking at the videos and notes, I mean, if you do it, looking at the videos and notes, okay, better if you do as little of that as possible, but sometimes you got it. Then you should be able to go back and do it without looking at it. Okay, so we do the okay. That's what it looks like. Distributive law over here. If you didn't write it out like this, you didn't do it right. Okay. If you didn't write it out like this and you had to what you thought you were going to get, you skipped a step. Okay. And did it by what you thought was going to happen instead of what does happen. So please write things out one step at a time. There's one thing you need to do here on the left side is apply the distributive law without skipping anything. Write it out literally, this times this minus this times this. Okay. Now, next thing, and it's kind of okay. A lot of people multiply 3 by 7. I wouldn't do that for the reason I'm going to show you. Okay, I'm going to write it out like this because we're multiplying fractions. I'm going to write this integer still in factor form, 3 times 7. It's a simpler form. 21 might look simpler because it's a little shorter to write out. And that's 2 digits also, but you got to write that dot, and that takes hours. No, it doesn't. Okay. You just multiply or put parentheses around it or whatever. It doesn't take long. And you do this. Okay. And then we have minus 3 times 7 over 1 times 3 over 7. Now, how can I rearrange this? Now, what you want to do, and it's okay to want to do it, that 3 should cancel that 3. And that 7 should cancel that 7. Okay? There's an advantage to thinking about cancellation, but when you don't totally understand the rules, multiplying fractions, and especially for canceling, because the rules are a little more complicated there, you want to be able to rearrange these so you see why it cancels, so you can always justify when you want to cancel. Okay, so you look at this, you say, well, that 3 should cancel that 3, that 7 should cancel that 7, and you cross out this 3 and this 3 and this 7 and this 7, and you're wrong. Okay, and people will do that. Almost everybody will do that given the opportunity if a problem is written out so it looks like you ought to do that. You can't do mathematics by what it looks like. You got to do mathematics by the rules. It's okay to think about what it looks like and then use the rules to see if you can make it do that. Okay. So our impulse here is, and of course, open math is going to tell you to cancel those. Okay. Because they think you know how to cancel. Okay. Our schools are not teaching people to cancel. It just isn't happening. Less than 10% of the people come out of Algebra 2 understand cancellation. They just do it. Okay? And they make mistakes. Usually they do it right, but they make mistakes because they don't really understand. Which is why I'm putting you through all this pain. Okay? Not to punish you for sins of the whole educational system, which are much worse after COVID. Okay? But because you need to be able to do these. And you need to be able to do them reliably. Okay, well, again, you look at this, you multiply by the 3 and 7, and that's going to clear the 3 and the 7. That's going to clear the denominators. You just have to do it carefully. Okay? When you get it in this form, yeah, that 3 cancels that, and that 7 cancels that, but make sure you understand why. Okay, so you can rearrange this. This is the same as 3 over 3 times 7 over 1 times 5 over 1 times x. I'm debating about what I really wanted to write it that way, but yeah. Okay. And then this is minus 3 over 1 times 7 over 7 times 3 over 1. That's 189. Now, all I did was I've got 3 numbers in the numerator here, not counting x. And really, you should probably write that as x over 1. Just to emphasize that x is in the numerator. So at least 2 people write this out. When they get to this, will that x look like it was attached to that 3 in the denominator? You want to be real careful about that, okay? Make sure you understand what's in the numerator, what's in the denominator, and you can emphasize that by writing x over 1 instead of x. So we can expand it like this. This is very simple. We see that this is the same as this. It's got exactly the same numbers in the numerator. It's got exactly the same numbers in the denominator. Now, you know, we introduced some ones there, but you can put as many ones as you want into that denominator as long as you multiply. We put them there to keep track of what the numerator is and what the denominator is. Okay. Well, then we notice that 3 over 3 is what? So we got 1 times 1. Well, we can multiply 7 by 5 and x. We can always multiply the numbers in our numerator. We could have multiplied them here, got 105. And then we could have 105 over 3. Then you have to go to your calculator and divide it. You don't need a calculator. Write out the factors. It's going to be very important when we get to doing this with symbols, with rational expressions. You don't know what that is right now, but it's one of the hardest things in pre-calculus. Okay, one of the hardest things you're going to encounter in algebra. You want to compare it by understanding what's going on with numbers. Then, once you understand it, it becomes much easier to do it with symbols. Okay. Okay, well, anyhow, here we go. And then here we got this. Now, all these ones, this leaves us at 35x, because any multiplication or division by 1 is not going to change anything. And over here, we got 1s in the denominator. We got a 1 in the numerator. And that's just going to be then 9. That's 189. And notice here, the same place we were here. Now, if you understand and believe all these intermediate steps, you can go directly from here to here. You got just writing out the left-hand side. The right-hand side hasn't changed since here. Okay. You can see that you're going to have the 3 over 3. And then that's times 35x. Get the 3 over 3. The 1 doesn't have to be there if you don't need it. 7 times 5 times x is this. And maybe write that 35x over 1. And then this is minus Order. 3/3 justifies crossing out these threes. Okay. Get 35x. 7/7 justifies crossing out those sevens. There's our 35x minus 9. In fewer steps. I didn't write out all this stuff. It looks a little bit complicated, but you really want to be able to think through this to assure yourself that when you are tempted to cross these out, it really works. I want you to at least write this much. For to see all of this, but that can get a little hard to look at. Try to understand it if you can, at least be sure you understand this. Now, the whole thing is, when I multiply by 3 times 7, when I multiply 5/3 by 3 times 7, I just end up with 35, right? Of course, I've got a dx along there. When I multiply 3/7 by 3 times 7, I end up with 3 times 3. Okay? Comes down to something that simple. Now let's see. We've got about 30 more minutes. So I want to spend no more than about 5 minutes doing this. I'm not going to finish this because the rest of it, everybody does that. Okay. Nobody has any trouble once it's in this form. I just said, I just kind of digress back to this problem. I wrote 3 steps, start here, and we get this, this, and this, and we get this very quickly. And it's in some ways easier, especially if you have your calculator handy. Okay. So you write this step as 21 times this. And you multiply 21 by 5/3, 21/1 times 5/3 gives 105/3. 21/1 times 3/7 gives us 63/7. And then 3 divides into 125, and 7 divides into 63, giving you this. It's a quick way to get the answer. But if the numbers are kind of big, you're going to need a calculator. And when you get to rational functions where it's all symbolic, calculator's not going to help you anyway. Okay. Then you have to factor things that were already factored if you wrote it out this way. Now, you don't necessarily understand what I'm talking about, but that's the reason I really don't want to see you do this. I want to see you do this, at least this, preferably all of this. Okay. Now, we have an equation like something over x, let's say 7/x plus 2 equals 25. Their equation will have different numbers in it. It's the same idea. What's the rule? Underline both sides. You multiply both sides by the denominator, not just the thing you're focused on, both sides of the equation. That keeps the equation in balance. You've heard me say that a number of times. And you're going to write it down here. Keeps the equation in balance, meaning you multiply both sides by the same thing, then they stay equal. If you multiply just part of one side by that thing, they're not going to stay equal. And you're going to get an incorrect solution. Okay, so we multiply both sides by the denominator. What's the denominator here? It helps to circle the denominator because some people wanted to multiply by that 7. And what you're doing if you do that is you're multiplying that thing with x by both sides. Okay. And multiply that thing with x by both sides. Well, that thing with x is in the numerator and x is in the denominator. It's not going to help. Not going to get you anywhere. X is still going to be in the denominator. Now, if I multiply both sides by 7, I'd still have a true equation. But x would still be in the denominator because 7 over 1 times 7 over x, okay, is 49 over 7x. X doesn't come out of the denominator that way. It does come out if you multiply both sides by x. So I say, okay, we multiply x times 7 over x plus 2 equals I'm writing it out the way you wrote it out. Now, I'm not blaming you. I just wrote it that way. Okay. And since you got fractions involved, I want to write this as over here. Just to emphasize, it's got a numerator and a denominator that multiplies numerators and denominators over here. So we have x over 1, 7 over x. Plus x over 1 times 2 over 1. In other words, it's x times 2, but we write it as x over 1 times 2 over 1. And this equals 168. Okay. Well, this can be written as x over x times 7 over 1 plus 2x over 1 equals 168. And this is clearly 1 times 7 over 1 plus 2x equals 168. So we have 7 plus 2x equals 168, etc. Now, right now, I want you to write out all these steps, but when you understand all these steps, you just pretty much get from here to here in one step. You can do it in your head. X over 1 times 7 over x. Well, that's x over x times 7 over 1. X over x is 1. And that's why we multiplied by x. And 7 over 1 is 7, so we get this. And then x over 1 times 2 is pretty clearly 2x. And 7 times 24, so we get from here down to here quick. These steps here you need to understand this. And I want you to do it when you write these things out. But then it comes down to here. And if you do 50 of these problems, it'll pretty much be ingrained. Okay, well, I want to go to formulas. Talk about formulas. Well, we got 15 minutes left. That's the main thing we wanted to talk about today. But it's not unusual that people have to avoid fractions. I'm going to make sure I don't have any more fractions on the camera. Okay. So now we want to do some of the same stuff. I'm going to start out. I'm going to give you a few simple problems to work out. Probably won't give you real long to work on them. All I really want to see is the first step. Okay. And now I might use A's, B's, C's, D's, E's, F, and G's, but they don't have, if they don't have back apostrophes on them, they're just simple. I'm going to try to avoid using just because I'm going to put back apostrophes. But right now, I'm probably just going to use all symbols. So let's say we got start with this. I want you to solve this for x. Solving for x. What's the very first step? Now, if you take additional steps, even if they're wrong, you know, go ahead and take them. I want to see what you're thinking. But this gets solved in really just two simple operations. Okay. Some people have some it didn't, but it's pretty simple. If you have, let's just think of what you could do if these were numbers. If this was this, what's the first thing you would do? In terms of operation. Yeah, exactly. Okay. Okay, so that's really quite simple. These are not your numbers A, B, and C. These are just symbols A, B, and C. They don't have backward apostrophes. Okay, people did pretty well here. But at least one person subtracted B from both sides. And normally I say do additions and subtractions before you multiply, right? The whole idea of multiply by the common denominator supersedes that. Okay. You do that before anything else. Usually. Right now, you do that before anything else. If you subtract B from both sides and then multiply by the common denominator, you're still going to get it. Okay, it'll be fine. So it really doesn't matter, but I want you to have kind of a brief thing. I almost wrote down just C over there, I didn't multiply both sides. That's concentrated on this. That's where my focus was. And I got careless. Now, when I looked at it, I saw immediately. Okay. But make a lesson. Okay. And you get A plus BX equals CX. Now I'm going to finish it quickly. Over time. So we have A equals BX CX minus BX. Okay. You still got to solve for X. I'm going to tell you what you do. Do this sort of thing a little bit later. A would be C minus B times X. So that's C minus B Actually, there's a just to get x on this side. We get x equals a divided by c minus p. I skipped a lot of steps there. But you factor out the x. We have to talk about factoring. And you can see that if you multiply this out, you're going to get this. So this works. And then you can divide by this. And that's an extra step of complication that you're not going to see in your homework. Okay. Homework is solving formulas. And you use the same operations that we've used when we have numbers. But with formulas, we have symbols. In some cases, that's simple. You don't have to worry about what the numbers are, just get the symbols in the right place. Okay. Okay. So this information is right there in your book. I don't know if you've read that far. I don't know if you needed it for the assignment you did, but everybody got good scores on the assignment. And I didn't see a whole lot of extensive guessing. Okay. I saw some mistakes, you know, we had to modify your answers a couple of times. I went through them all, you know. But on the whole, I'd like to see less error on the first try. But on most questions, you were getting them on the first try. So that's good. Make sure you're focusing on where are the principles and how are the principles being applied. Now, it does give you these four equations and more or less this form. I'm not sure that x naught is always grouped with x out, but it should be. So if your book didn't do that, write them and tell them Dave said you need to fix them. Okay. In any case, these are the four equations. These two come directly from the calculus. Start with the assumption of uniform acceleration, do two integrations, and you really need to understand that because we spent a whole week doing it. The very first with omegas and alphas and thetas, and then we transitioned to x's and a's and b's. Okay, so they're the first two equations. Formally, you could eliminate x between these two equations to get this one, and you could eliminate acceleration between these two equations. Solve this for acceleration, substitute it here, simplify it, and get this. Okay, and the magic of this is if you know any three quantities, and the three quantities I'm going to say we've got five quantities here. We've got xf minus x naught. I regard that as one quantity. Scheme doesn't work if I don't. And that's really often x naught is going to be zero anyway. But that's just one quantity. Then you got p naught x, pf x, AX, and T. If you know any three of these, you can use equations to find the other two. So any three equations via the other two, and you don't have to do simultaneous equations. All you really need is the first two equations, but you would end up having to do a lot of simultaneous equations if you just use these. Calculus gives you these. Technically, it's all you know. But there are operations that you would have to do, eliminating t between two sides, or the two equations. And you get this one, eliminate acceleration between these two equations, and you get this. And since you would end up doing that all the time, we just write down these two equations, which have direct physical meanings they're in some cases easier to understand than the physical meaning of this equation. This one's pretty easy. Multiply the acceleration by the time, it tells you how much velocity changes. That's what acceleration is, rate of change of velocity. It's constant, you just multiply that constant acceleration by time, you see how much the velocity changes. And add that to your initial velocity, and you get the final velocity. Okay. Okay. That's very simple. This one is very simple. If you understand that if acceleration is constant, the velocity graph is going to be linear, and the average value of a linear function between 2 points is the average of the two, the initial and the final values. And you're just averaging the initial and final velocities to get the average velocity. That doesn't work if you have non-uniform acceleration. And you should really understand that by understanding the whole idea of the average value of a function in calculus. Okay? And you want to continue to think about that. But again, if the graph of v versus t isn't linear, this isn't the average velocity. We'll talk about that. Okay? But you multiply the average velocity by the time, you get how far you went. This is how far you went. Well, it's your displacement, which is how far you went and whether it's positive or negative. Displacement's a vector quantity. Distance is just how far you went. It doesn't matter if it's positive or negative. So we don't really use distance, we use displacement. This is displacement. Okay, well, in this case, just say yes or no. Okay, say it as quickly as you can. Do we know the displacement of the ball going up the ramp? Do we know the displacement of the ball going down the ramp? Yeah. Okay, do we know the initial velocity of the ball going up the ramp? You know its final velocity, it stops, or it starts coming back down. We don't know its initial velocity, it's going to have to find it. So in one case, we know the initial velocity. Well, we know the final velocity. Okay. What about coming down? Do we know the initial velocity? Yes or no? What is it? Yes. Okay. Do we know the final velocity? See thumbs. Okay. Now you're shaking your heads. I can interpret that as a thumb, but don't confuse your thumb with your head. Okay. No, it's fine. I understand. You understand that. Okay. So going up, we know the displacement. Did I ask you? Do we know the displacement going down? I think I did. You said yes. Yeah, we know the displacement both times. In one case, we know the initial, and in one case, we know the final velocity. That's two things. Okay, what else do we know? Use your fingers. Maybe you have to have two hands. That's the displacement. You estimated it. Time. Okay, you got it right there. Okay. So in all cases, we know this and we know this. In one case, we know this, in one case, we know this. What we don't know is whichever one of these isn't zero, okay? So maybe in one case, we know v naught x, and that's sufficient to find the acceleration. In the other case, we know vfx and t, and that's sufficient to find the acceleration. And also, we can find vfx. In this case, we can find v naught x. In this case, now the arrows get really complicated. But it's really very simple. You find an equation that contains the three variables that you know, then solve for what's left. There is an equation. If you know xf minus x naught, dfx, and t. So you know this one, the middle one, and this one. Okay. Then which equation contains those three? There are four equations. 1, 2, 3, or 4. Tell me what you think. Can you find an equation that contains this, this, and this? Got it. Okay. 4. 3 doesn't. 3 contains this. 3 contains this. But it ain't contained in T. So you've got two things unknown in this equation. You can't solve an equation for two unknowns. Now, if you got two equations, well, you can always use these two equations. Any combination of 3 can be substituted in these two equations. But in many cases, you'd have to solve them with simultaneous equations. Use these equations instead. Okay. So identify the equation. That's a good place to start. You know the displacement. You know the final velocity. You know the time. You know that for the first phase, for A1 or for phase 1. You should be able to solve those equations. I'm going to work this out and give you some comments. A little clumsy writing the 1s and 0s and F's and all that stuff. I got confused with writing the darn things myself. So you want to be careful. So since we're talking about a phase 1 and a phase 2, we got to use subscript 1 on all these variables. And I didn't do it here either. Verify it. Okay. So it's xf minus x naught. Okay. We're going to make that x1 x, f, and x1 0. And then over here, it's going to be v1 0x and v1 fx. Okay, so it's v1 0x, v1 fx, and t1. Well, those are the symbols. So I'm going to replace these things by their quantities. Now, that's not actually the way you often want to do these, but I'm going to do it anyway. So if this is 60 centimeters, that's going to give you 60 centimeters equals what? V1 0x plus 0 over 2 times T1, which we know to be 4 seconds. Oh, that gives us 60 centimeters equals V1 0x over 2 multiplied by 4 seconds. And something else that I don't really need to do. But we end up with V1 0x equals 60 centimeters over 2 seconds, which is 30 centimeters per second. Okay. And I've carried the units all the way through. When I divide the 2 into the 4 seconds, I get 2 seconds. And to get V1 0x, I'm going to divide 60 centimeters by 2 seconds. So if I put a wrong quantity in here, if I put an acceleration in instead of a velocity, or let's say I put a velocity instead of a displacement. So I'd have centimeters per second here divided by 2 seconds, give me centimeters per second squared. And I know that's not a velocity, so I know I did something wrong. Velocity is not measured in centimeters per second squared, it's measured in centimeters per second. And we understand the reasons for that as deeply as possible. Okay, well, actually now, the way I would really do this is I would say, for phase one, eliminated all the subscripts so I don't have to keep writing them and getting confused. Okay, and we solve this. But we know what else. Well, I'm just going to put 3 dots, but how do we solve it? We multiply this by 2 over t, multiply both sides by 2 over t to give us v naught x plus v fx equals 2 over t times this. And then we subtract the one we don't know from both sides. Okay, in this case, what is it we don't know? We don't know v naught x. So we get this. And this equation hasn't been. This is going to equal 2 times 60 centimeters over 4 seconds minus 0. Okay. Or 0 centimeters per second if you want to be really strict about units. And if you want to be right, you probably want to be very strict about units right now. Okay. And that's 30 centimeters per second. And the only place I have to mess with units is in my substitution. And I make sure that this term and this term both come out in centimeters over seconds. That's a check. It's not a complete validation because you can get the wrong thing in there and still have the right units. Okay. But it's validation of the process. It also causes you to think a little bit about what these things mean. Now, for example, what does this 2xf minus x naught over t give you? Well, it gives you 30 centimeters per second, which is your average velocity. Okay. Knowing that vfx is 0, because you say, well, okay, v naught over 2 is the average velocity. I'm sorry, we could have said that I know the average velocity is total displacement divided by the time. Because acceleration is uniform, we could have shortcut this a little bit. Okay. There's a lot here, but the basic idea is, and the way your book is going to stress it, you take the equation, you figure out you find the equation that works for the 3 things you know. You solve it for the variable you want, and then you plug in. And you check the units. You make sure it's dimensionally consistent. There are other ways to do that. They say, well, okay, this is in units of length, this is in units of time, so this is units of length divided by units of time, and that is units of velocity. Okay. The book doesn't tell you to do that. Well, you can do that. And if you're very rigorous about it, I still like writing out the units, especially early in the course. Because if you don't, you're going to almost certainly make mistakes that you wouldn't otherwise make. And as engineers, the bottom line is put the blank thing right. Preferably by understanding the steps and thinking through it, because that's the most reliable way to get things right. Okay. Okay, that's here. Now, hopefully you wrote down the equations. Did you write down those equations? Wrote them on the board? Everybody got them? Actually, I better keep this. Need it. Okay, so now we've got final velocity for phase one. How to get the acceleration. Okay, let me just point out, I said, okay, which equation are you going to use? And people are sitting there thinking, I'll let you know with the equations. You will be by the time we meet again, because you will have had to use them to solve a lot of problems. If you haven't already. But at this stage, we've calculated the initial velocity for phase one, right? So we can complete phase one by just finding the acceleration. And we know 4 quantities now. We know everything but the acceleration. Well, it means we can find any equation up here that contains acceleration, this one, or this one, and solve for the acceleration. Now, which one is simplest, first, second, or third? Yeah, okay, first. Okay, so, so we know all this for phase one. And the equation with AX can be solved for AX because there are only 5 quantities. If you treat XF minus X naught as its own quantity. So, which equation is the most obvious? Everybody said the first one. Well, use the first equation then. Think about what it means. Go ahead and solve the first equation for AX. Calculate it and tell me what your result means, and also how you could have just used simple definitions to do it without having to even think about the equation. Okay. First equation is the easiest. So you get and that's very straightforward. You subtract this from both sides, divide by t. And that equals I really want to see the units, not just numbers, not just tacked on at the end, at least in this calculation. And that's going to be minus, in my case, we subtract what we just did, It's 4 seconds up, so it'll be 30 centimeters per second. It's negative 7.5 centimeters per second squared. Centimeters over second times reciprocal seconds is centimeters over second squared. And now we solve that. Okay. Now coming back down, well, you can solve that equally easily. Okay. And you're going to get a slightly less, so you're going to get slightly less acceleration. I got something closer to 5 seconds coming down. I figured it's about 4.8. If it's 5 seconds coming back down, then, and let me comment here. Or AX equals delta BX delta T, and delta BX was this. Okay, because really all this equation is saying is this. Because why? Because here's your delta B. Okay, this is just delta Vx over delta T. So you just take the definition of average acceleration, which is delta this over delta that. Okay. And you immediately get this equation. You don't need to integrate anything. But of course, if you have a non-uniform acceleration, you do need to integrate. So it's important to understand how these simple equations come out of integration. But there's an intuitive connection. That's just the definition of velocity. Okay. I'm sorry, definition of acceleration. And this is just definition of velocity, average velocity. So this equation and this equation could be regarded as the fundamental equations because they're the simplest. So this is this equation just for uniform acceleration. If acceleration is linear, if velocity is a linear function of time, acceleration is constant, then this equation is just this equation is just this. And sometimes you can just go intuitive and use these equations. If you're sure acceleration is uniform. If not, you're into polynomials, good luck. Okay. Okay, well, that's a lot of detail on one instance where we can use the equations. Okay, so I'm just going to do a quick analysis for phase 2. I'm going to say that, okay, let's see. In this case, we know x equals 0. Acceleration is uniform. What is xf minus x naught coming down the incline? Xf minus x naught. Now, Remember, we've fixed the x-axis. Now implicitly, x was 0 at the starting point of the first phase, right at the bottom of the incline. And the x-axis is up the incline. So our displacement, second, is from here to here. That's in the negative x direction, isn't it? Now, if you're careful about what x means, x out. X out minus x naught is, well, this phase ends at x equals 0. It started at x equals 60 centimeters. So the displacement is negative 60 centimeters. So people wanted to say, well, 60 centimeters again. Well, the magnitude is going in this direction, and the direction is critical. So make sure that you know what axis you're using, or in 2 or 3 dimensions, what axes you're using. And if you're going to keep those axes the same, by darn, keep them the same. Okay, and measure relative to those axes. Okay, so then, I got to very close to 5 seconds. I thought it about 4.8. It was about that far from the end when I got to 1,004. But I'm not sure I was really counting consistently. I think I was pretty good at keeping a constant rhythm. But when I'm watching things and trying to observe other things, you can't be sure. So, naturally, we could use Audacity and get this really accurate surface. So you do significant figures, okay? Okay, so t equals 5 seconds. So now, just intuitively, average velocity is negative 30 centimeters per second. I just averaged 0 centimeters per second, negative 60 centimeters per second. No, no. It's delta V over delta T. Sorry. Different information. Okay. It's kind of shortcut thing. Now you want to run it through the equations and make sure you understand why the shortcuts are working. But in this case, VF is 0. Or it's VF. These odds at 0. Push it down. Okay. Something's not firing right in my brain. The average is not negative 30 centimeters per second. Negative 12 centimeters per second, right? You divide negative 60 centimeters by 5 seconds. Negative 60 centimeters over 5 seconds, you get the negative 12 centimeters per second. And you get negative 24 centimeters per second. And now, taking this, down the number that I see there, other than the number that I just got. Okay, so your delta B is your BF minus B naught. Wait a minute. Yeah. Oh. Final velocity minus initial. And you get negative 4.8 centimeters per second squared, as opposed to negative 7.5 centimeters per second squared. You got phase one. Okay, now the board is kind of a little confused, so I'm going to put an orange circle around phase two. Everything in the orange circle is phase two. Phase one kind of stuck its nose into the space I needed for phase two. Okay. Now what I just did, and I wrote a lot of things down wrong because I'm not clicking. But for phase two, we know that the displacement is negative 60 centimeters. We know it took 5 seconds. So if we divide the negative 60 centimeters by 5 seconds, we get the average velocity. Well, the average velocity is the average of the initial, which is 0, and the final, which is negative 24 centimeters per second. Or not, yeah, negative 24 centimeters, negative 12 centimeters per second. Sorry. Okay, again, the average velocity is, I said it wrong again. The average velocity is the average of the initial and final. Okay. Since the initial is 0, then the average velocity is just going to be the final divided by 2. Now that only occurs if the initial is 0. Okay. You want to be careful about that. You want to use the equations carefully and not make a bunch of assumptions. But this is a quick and dirty calculation that you can verify with the equations. And this is intuitive. Okay. Average velocity is the average initial and final. So if the initial is 0, final's got to be double the average. There's a graphical representation of that too. So we conclude that the final velocity is negative 24 centimeters per second. And then the acceleration is change in velocity. Well, the change in velocity is just the final velocity since it started at 0. You divide that by 5 seconds and you get this. It's 2 simple calculations. 3 very simple calculations. Now, you plug it into the formulas to justify all that. Because once people see, oh yeah, the average velocity was the final velocity divided by 2. Now they take that as an equation written on a stone tablet, forgetting that it required the assumption that the initial velocity be 0. Okay. And then all kinds of chaos ensues. Get ridiculous answers if your initial velocity wasn't 0. So you always go back to these equations to check. But sometimes you do a quick back of the envelope calculation and get it. And in this case, if you do it carefully, it works. Now, the thing here then is, I want to talk about this a little bit. Okay. Now, what we're really focused on here is using the equations, identifying our variables and so forth. And your homework is going to amply reinforce that. Why is the acceleration different going up than going down? Okay, well, the thing that's different, the acceleration, the component of gravity parallel to the incline is the same going up as down. Okay, doesn't make any difference going up or down. So gravity really kind of has a very similar effect in both cases. It's slowing things down. Why is it that you have different acceleration here? It's because you have friction. Rolling friction with the ball along the incline. And rolling friction, when you're going up the incline, this friction help. This friction, you more acceleration or less. Okay, right, more. Okay, more meaning a greater magnitude of the acceleration. It wasn't. Okay, look. Acceleration is in this direction. You're rolling up the incline. What's the direction of friction? Well, friction opposes motion. What's the direction of motion? What's the direction of friction? Right, back down. So friction is enhancing the effect of gravity in slowing the ball down. If you want to be intuitive about it, and you do. Okay. Now, ball starts coming down. This is a little less intuitive. What's the direction of the gravitational component parallel to the incline? Still down. Gravity is trying to move that ball down the incline. Okay. What's the direction of friction? Well, friction is resisting the motion. Okay, motion's in this direction, friction's in this direction. Comes out less. And from this, we can obtain what we call the coefficient of rolling friction. And that's the analysis I want you to do with that pool ball. Okay. Now, a couple of other things just to give you the framework here in 5 minutes we've got left. This is a if and only if sign. Constant acceleration implies linear velocity, and linear velocity implies constant acceleration. If you integrate a constant acceleration, you're going to get a linear velocity, at plus v naught. Okay, integrate a, you get at plus a constant. Constant should be naught. Linear velocity. Okay, and that's equivalent to quadratic position. Now, if I wanted to write it out completely, and I would like to, but I don't have time, velocity is linear in time. Velocity is a linear function of time. And position's a quadratic function of time. Okay, so now. Constant velocity is equivalent to zero acceleration, right? Your velocity is constant, your acceleration is the rate of change of velocity, and constant ain't changing. Or if you wish, the velocity is a constant, you take the derivative to get the acceleration. So it's the same thing I just said. So make sure you understand why those two statements are equivalent. Okay. And now constant velocity means linear position. Okay. So if your position is linear, the velocity is constant. Acceleration is zero. So what does this straight line graph tell me? If x versus t is a straight line, what do I know? Well, apparently I didn't record all this, but you have a constant acceleration, that's equivalent to having a linear velocity. Why is that? Well, the calculus of it is, if your velocity is linear, then since acceleration is a derivative of your velocity, it's going to be constant. Acceleration is just some multiple plus some other number. So, and alternatively, you go from acceleration to velocity by doing antiderivative, and your general antiderivative of a constant is a linear function. Okay, antiderivative of a with respect to t is at plus a constant, and then we identify that constant as initial velocity. And then similar relationship here. You take the derivative of a quadratic position function, get a velocity function, or you integrate a linear velocity function to get your quadratic position function. All that should be pretty obvious. Similarly, if your position function is linear, then your velocity is constant. And if your velocity is constant, your acceleration is zero. So if you've got zero acceleration, you'll have a linear position function, constant velocity. And then I use the example of, okay, here's a linear function. This represents the position of the guy that goes by me as I'm making a right turn onto a road. Now let's assume it's a two-lane road, so I don't have to actually collide with the guy to catch him. Okay, so here's the graph of this guy's position. Okay, constant velocity means that give this guy the subscript 1. So xf1 equals v naught 1 t plus x naught 1. Okay, just xf equals v naught plus x naught, v naught t plus x naught. But we put the subscript 1 on here to distinguish his motion from mine. So there it is. X naught 1 is, of course, if we take t equals 0 to be the instant at which I pull out, then that's his position as he goes by me, or maybe shortly after he goes by me. That's his position. It's the initial instant. My position I take to be 0 at the initial instant. I'm going to accelerate constantly, even though cars can't easily. It's not easy to achieve constant acceleration with your car. Although if you practice watching your speedometer, if you get your speedometer moved at a constant velocity, then you're doing constant acceleration. It's very unnatural. Car produces more or less constant power, which doesn't give you constant acceleration because the distance through which you accelerate multiplied by the force you exert, is your power. And the faster you go, the more distance you have to travel in order to increase your kinetic energy and all that stuff. It said it better, but it's hard to accelerate a car and try it on an isolated road where there's nothing else to run into. And just, keep glancing your speedometer and see if it's going up at a constant rate. It's not natural. Okay, so anyhow, so I accelerate constantly. Let's assume I accelerate constantly. So my function, I'll call it xf2, is 1/2 a2t squared plus v02t plus x02. My v02 is 0. I'm starting from 0 velocity. The slope of my position curve is 0 at this instant. So v02 would be 0. X02 would be 0. So my position just be 1/2 a2t squared. More generally, if I have some velocity when this occurs and some position, well, this equation accommodates whatever the conditions are. Okay. If I want to know when I catch this person, I set this function equal to this function, because this function is this curve. This function is represented by this curve, and where they cross is where our positions are equal. And there's some time at which that occurs. So I solve xf2 equals fx1 to find t when I catch up. Now there's more I can do, but once I know the t when I catch up, I can plug that t in here and verify that my positions are equal. I can take the derivative of this function and get my velocity function and plug t in, so I can find out how fast I'm going when I pass it. Of course, I can use one of my equations of uniform motion to do that. Well, this is a general situation, something that's a little more difficult in our first chapter on uniform acceleration. Okay, it's mostly the uniform acceleration. Last section gets into non-uniform acceleration. If acceleration is non-uniform, then I don't have constant acceleration. My velocity is not going to be linear. My position function is not going to be quadratic. We'll probably end up at polynomial of some kind, and that gets a little more complicated. The calculus is easy, but solving the equations gets harder. Okay, so that's a framework for some of the stuff that you're going to see in more detail. I also recommend, and I should have said this in class, I didn't, and I got a recording on when I did this. I'm doing this after class. Something I really want to emphasize to people: watch these video tutor things in your text. These demonstrations are extremely valuable. They're short. They give you a picture of things, and they make you think about the physics in a way you don't think if you're just searching for equations and plugging things into the equations, sometimes right, sometimes wrong when you're at the beginning. Get those pictures, and of course, you have the hands-on stuff in the lab. And one little bit of homework for tonight, of course, is to repeat the analysis we did over here, where we looked at the difference in acceleration between phase 1 and phase 2. We talked a little bit about why that happens. I want you to repeat that for the pool ball data, where you estimate the positions of the pool ball. Just take your best guess how far the pool ball is. Figure out how many feet, change that to centimeters, calculate your acceleration, or meters, whatever.